Now that we've solved one-dimensional Schrödinger equation problems, I'd like to back up and talk about quantum formalism. We'll start by noting the equivalence of quantum mechanics and wave mechanics to linear algebra. Then we'll talk about Hilbert space and define Hilbert space, talk about the inner product, and then look at the properties of Hilbert space. So, quantum mechanics and wave functions are mathematically identical to vectors in linear algebra. Say we have a wave function alpha. This is equivalent to a vector A, where A spans a space of n different parameters. Wave functions have inner products. We'll define the inner product a little bit later. It's written like this, with you have a bra alpha and a ket beta, and that's equivalent to writing the product of two vectors, which becomes a scalar. So that's a scalar product. It's A1 star B1 plus A2 star B2 and so on to AN star B sub n. Operators act on wave functions. This T operator will act on alpha in the same way as a matrix, which is a linear transformation, acts on a vector. So T is now here a matrix acting on a vector A, and the T matrix is an n by n matrix, and the vector is an n row vector. Because of these similarities, we can write down a bunch of properties immediately. We can write down that we can add vectors. So alpha plus beta is equal to gamma. We can write down that addition of vectors is commutative. That is, alpha plus beta is equal to beta plus alpha. We can write down that it's associative, so that I have alpha plus the quantity beta plus gamma. It's equivalent to alpha plus beta quantity plus gamma. The null vector exists. If we take alpha, we add to it the null vector 0, we get alpha back. And then alpha and every vector has an inverse, so that the inverse of alpha is minus alpha, and that's equal to 0 when you sum them. So you take alpha, you add the minus alpha vector, and its inverse, and then you get 0, the null vector. We can also bring in the vector properties that are related to scalar multiplication. So you take A as a scalar, you multiply it times a vector alpha, or wave function alpha, and you get gamma, a new wave vector. It's distributive, so that if I have A multiplying alpha plus beta vectors, then I can rewrite that as A alpha plus A beta. And you can also distribute scalar addition through a vector, so that A plus B times alpha is equal to A times alpha plus B times alpha. Scalar multiplication is also associative. That is, if I take A times the quantity B times alpha, it's equal to A times B applied to alpha, multiplied to alpha. And we get the null vector by multiplying times 0. And we have an identity when we multiply times 1. The constant 1 just gives you the vector back again. And finally, we can learn a little bit more about the inverse. The inverse of alpha, this minus alpha ket, is equal to minus 1 times alpha, or minus times the ket alpha. So the difference is that you cannot have vector multiplication be associative. And it's not commutative, because we know that commutation relations are not necessarily 0. All right, So unlike in linear algebra, wave functions aren't defined on an n-dimensional space, but on an infinite dimensional space of the continuous variable x. And so we have to treat things a little bit differently. This means we have certain restrictions when we use the language of linear algebra for quantum mechanics. The first thing is that a physically meaningful wave function must be normalizable. That is, you can take the square integral over all space of a wave function and you must get 1. Therefore, your vector space for wave functions is the set of all square integrable functions f of x on a specified interval, such that the integral of f of x modulus squared integrated from a to b has to be less than infinity. Otherwise, you can't have normalizable functions. In quantum mechanics, this is called a Hilbert space. And all wave functions exist in a Hilbert space. So Hilbert space is a set of square integrable functions. Now we can also define something called an inner product, which we mentioned before. The inner product of two functions is, or two wave functions, or two of these vectors, is written as ket f, bra f ket g, and that's equivalent to the integral from a to b of f of x star times g of x dx. And that's the inner product of f and g. So let's look at a little bit more carefully at the results of what this inner product does. If I take the inner product of g with f, it's basically this integral from a to b of g star f dx. But I can rewrite this as the integral from a to b of f star g dx, all taken complex conjugate. Because the complex conjugate won't change dx, but it will change the f star to an f and the g to a g star. But this is simply the inner product of f and g. And so what we're saying then is that inner product of g and f is equivalent to the inner product of f and g complex conjugate. So if this is a real number, then this is going to be an identity. They're going to be equal. The inner product of a function f of x with itself is from a to b, is the integral from a to b f star f dx, or the modulus squared, the integral of the modulus squared of f dx. And this must be real, non-negative, and 0 only when f of x equal to 0. Right? This cannot be 0 if f is a real function. F of x, let's suppose, is normalized if the inner product with itself is equal to 1. That's just a normalization integral. And two functions are orthogonal when their inner product is 0. That is, we take two functions, f sub m and f sub n. We take the inner product of these two functions. And if that inner product is equal to a Kronecker delta, delta of mn, then they are said to be orthonormal. That is, they're orthogonal, and this gives you a 0 when m is not equal to n, but they give you a 1 when m is equal to n, so you have delta of nn is 1. So a set of functions is complete if any other function in the Hilbert space can be written as a sum of this complete set of functions. That is, if I can write h of x as a sum over from n equals 1 to infinity of c sub n times f sub n of x, then this is said to be a complete set of functions, f sub n, as long as this can be any arbitrary function that lies in the Hilbert space. So in this case, f of n spans the Hilbert space, and h of x lies in the Hilbert space, and it's just written as a sum of any functions. We've seen this before. This is just a little bit more formal. And C sub n are coefficients which you can extract by taking the inner product of f sub n, the nth function that spans the space, applied to h. And we take the inner product, we get this coefficient C sub n. Finally, let's look a little bit more at properties of the Hilbert space and inner products. So an inner product is guaranteed to exist in a Hilbert space if all its functions are square integrable. That is, if the sum of any two functions in a Hilbert space is also a function in the space. For example, let's take a function q of x, which is the sum of two functions, g of x and h of x. Now, each of these functions is in the space, and therefore it can be made up of the set of functions f sub n which span the space. And so I can write g of x as b sub n times f sub n of x summed over n. And I can write h, just like I did before, as a sum from n equals 1 to infinity of c sub n f sub n of x. Well, if you look at this, you can now, because of the properties of these vectors and the fact that these are scalars, I can take these and rearrange those sums and get just a single sum. So I can get a single sum from n equals 1 to infinity of b sub n plus c sub n, which are constants, times f sub n of x. But these two constants summed together are simply another constant, and they must be the constants that define q. We can write those as a, so q of x is also made up of the same functions that span the space. That is, the sum from n equals 1 to infinity of a sub n f sub n of x. And therefore q is also a function in the space, if these two are functions of the space, because it can all be made up from the same functions that span the entire space in our complete set. The modulus squared of q, therefore, if I write from this perspective, is g plus h star times g plus h. And that can be written by expanding as you have g star g, which is g modulus squared. You have h star h, which is h modulus squared. Then you have g star h, which is here, plus h star g. And so you have four terms from modulus squared of q. So you can take the square integral. If you take the square integral of q of x, then you can write it like this. The integral from a to b of the modulus squared of q dx is equal to the modulus squared of g integral of modulus squared of g dx plus the integral of modulus squared of h dx plus these cross products, the integral of g star h dx plus the integral of h star g dx. The first two terms are finite by definition, because both g and x are defined as being part of the Hilbert space. What we don't know is whether these two are. But there's something called the Schwarz inequality, which states the following, and limits these two integrals. It says that the absolute value of the integral of g star h dx is less than or equal to the square root of the square integral of g of x times the square integral of h of x. And so because of this, since these two are bounded and finite, then this must be finite because it's less than the square root of this product. And if this one is finite, then it's the one that's h star g is equivalently finite because it must be also less than the same product of the two square integrals. This Schwarz inequality is something that you can prove relatively straightforwardly.